Hello everyone, welcome back to online video tutorial on hydrology and irrigation engineering. So today we are starting with module 5, that is canals. In this class we are discussing the design of canal by a Kennedy's method. So basically there are two methods of the design of canal. One is Lacey's method and the Kennedy's. So today we are covering the Kennedy's method of design of canal. So in this Kennedy's method, so he have carried out a research work. Basically, a Kennedy carried out a research work so that to obtain a stable, non-silting, non-scoring channel. Okay, and he have made a observation. So basically, he have carried out his research work in the Upper Bari Doab Canal system, and which is one of the oldest canal in Punjab, which is serving Pakistan. And on this canal system, so that is on the Upper Bari Doab canal system, so what Kennedy have selected, he have selected a number of sites on various channels, okay, so which are not required a silt clearance. So what he have done, so in the canal system, he have selected a point where there is no silt deposition, means so where you don't require a clearance of silt. So that particular the points he have selected, and also or other maintenance for about last 30 years. Okay, so the points which have not required maintenance and silt clearance for last 30 years, so he have considered those points in the canal system. And after considering that the flowing water which has a counteract some amount of friction against the bed of the canal, so what we know that already, so once the water starts flowing in the canal system, so obviously due to the water molecules and the canal bed, there will be a friction. Okay, so where that due to that friction, what happens, so there will be a formation of eddies. Okay, so due to the friction between, for example, if we take this is a particular canal. Okay, so if we consider this is a canal, this is the top surface of the canal, and due to when the water flows, due to the friction between these water molecules and this bed of the canal, so there will be a friction. So due to the friction, what happens, the eddies will form. So the eddies is nothing but the reverse of flow. So this type of eddies will going to form on the surface. So that eddies will be responsible for the silt suspension. So due to that eddies formation, so the silt suspension will occur. And also the eddies will also start from the side. Some eddies formation will be also occurs on the sides of the channel system. So as we know, usually the the cross section of the channel, always the cross section of the channel will be a trapezoidal channel. As we know, the canal, so usually the canal is constructed in a trapezoidal form, so that we know. So along with the bed, so usually the eddies formation is going to occur on the sides of the channel also. So that is, but these are from most of its horizontal part. So but eddies is usually from the bed. Usually the eddies is going to form on the horizontal surface. And this silt supporting power, so due to that what happens, so in the bed, so due to the the eddies which are formed on the horizontal surface, so they do not have a silt supporting power, because means which does not have a power to remove the silt. So that silt supporting power is therefore proportional to the bed width of the stream and not to its wetted perimeter, because the whatever the eddies is going to form, it is only on the bed of the channel. It is not going to form due to the side slope. So it is in occurs in the rare case. So that's why the silt supporting power will be directly proportional to the bed width, and it's not proportional to the, it does not depend on the wetted perimeter. And also, so based on the research work or the observations what he have made. So he have defined a critical velocity as a non-sitting, non-scoring velocity, and he have given a relation between the critical velocity and the depth of flow of water, that is V naught is equal to 0.55 d power 0.64. So where in general form it is written as V naught is equal to C into d power n. So, and in this particular equation, so it has been derived only on the basis of the observation on one canal system, because he have selected only Upper Bari Doab canal system. So he have done observation on only one canal system. So whatever the equation which have developed this particular equation, so this is derived only on the observation of one canal system. So you cannot apply this particular equation to those channels which are flowing in a sandy silt of the same quality or same grade as that of Upper Bari Doab canal system. So you can apply this only those canal system which are similar to the Upper Bari Doab canal system, that is nothing but which carries a sandy silt. So you cannot apply this particular equation to any other canal system. So so because of that, what Kennedy have realized later, the importance of silt grade on the critical velocity, because silt grade is a very important factor which affects the the velocity of the flowing water. So that's why he have realized what is the importance of the silt grade, and he have introduced a factor that is known as YAM, which is a critical factor. Which is a silt factor, which is called as critical velocity ratio, that is CVR in his equation. So the equation now it will become V naught is equal to 0.55 m into d power 0.64. So where m is nothing but the critical velocity ratio, which is you have considered. So which you have given the importance of silt factor, and this CVR, that is m. So critical velocity ratio is equal to critical velocity of the area divided by a critical velocity for Upper Bari Doab canal system, because as we have made observation on that particular system. So CVR is critical velocity of the area to the critical velocity of that Upper Bari Doab canal system. And he have also used the Cutter's equation. So for finding the mean velocity, see V naught is the critical velocity. So we have used the Cutter's equation. So to find out what is the mean velocity of the flow in the channel. So we know already. So like V is equal to C root RS, where R is the hydraulic mean depth, S is the bed slope, and C is the Cutter's constant, which is given by C is equal to 23 plus 0.0155 plus 1 by n divided by 1 plus of 23 plus 0.00155 s into n by root r. So this is the Cutter's equation, so which we have used to calculate the mean velocity. And so he have given a different C values, so based on the different type of silt and also different types of material. So first table what you're seeing, so this table shows the value of constant C for different material, like for light sandy, coarse sandy, coarse silt. For different material, what are the C values, and similarly the value of M for different type of silt. For example, for light sandy silt and coarser light sandy silt, what is the value of M? So these are the value of M for different material. And so according to this Kennedy's method, what is the procedure to design the canal? So let us see the procedure, how you're going to design the canal using a Kennedy's method. So here, to design the canal, we require some prerequisites, like so the equations which are used are continuity equation, Cutter's equation, and the Kennedy's equation. So these are the three equations which are used to design the canal. So and here the parameters which you should know to design a canal are discharge, N, M, S or B by D ratio, that is discharge, Manning's constant, sorry, n is nothing but your side slope, m is a that is CVR, that is critical velocity ratio, S is the bed slope, and D by D ratio is the width to depth ratio. So these are the parameters you should know. And depending upon, like, so there are two cases, two procedures. So basically, so the procedure to design a canal using Kennedy's method, so is divided into two categories based on the given value, that is whether the slope is bed slope is given or B by D ratio is given. So if bed slope is given, the procedure is different, and if B by D ratio is given, then the procedure is different. So let us see the first case. So this when a Q, N, M and SC is given. That is nothing but discharge, side slope and CVR and the bed slope. When the bed slope is given, what is the procedure? So the step number one is you have to assume a trial depth D in meters. Okay, step one is you have to assume a depth. So after assuming the depth value, second step is you have to calculate the critical velocity V naught using the Kennedy's equation. So the Kennedy's equation, V naught is equal to 0.55 m into d per 0.64. So you're going to calculate critical velocity. Step number 3 is once you get the velocity, use that velocity and the continuity equation to calculate the area of the flow using the continuity equation. So Q is equal to area into velocity. So area will be Q divided by velocity. So you will get the area. That is step number 3. Step number 4 is, so once you know this area, depth, and assume the side slope, that is nothing but N as half, that is half horizontal to 1 vertical or 1 vertical to 0.5 horizontal for alluvial soil. So you have to calculate the width, because you will be knowing area and you will be knowing depth. So use the, because as I have already told, the cross section of the canal will be trapezoidal section. So you can see here D is the depth, B is the width. So using the area and depth and N, assume the side slope. N, you can see that is the side slope. You have to assume it as 1 vertical to 0.5 horizontal. So you calculate the width of the channel using the area equation, that is A is equal to BD plus ND square. So step number 5 is to calculate the perimeter. P is equal to B plus 2D root 1 plus N square. So again, so after calculating the B value, calculate the wetted perimeter. And step number 6 is calculate the hydraulic mean radius, that is R is equal to A by B, because in step number 4, you're going to step number 3, you're going to calculate the area, and step number 5, you're going to calculate the perimeter. So after that, calculate the hydraulic mean radius. And step number 7 is you have to calculate the actual velocity using the Cutter's formula, that is V is equal to C root RS, where C is equal to 23 plus the same formula which we have already discussed. Okay, so use the Cutter's equation to calculate the actual velocity. So next, what is the step number 8? The last step is, once you get the critical velocity and the actual velocity, you have to compare those two velocities. If they are same, then whatever the depth you have assumed at the initial step, very first step, is correct. So if these two velocities are not equal, if critical and actual velocities are not equal, then what you have to do, you have to reassume the depth value and you have to repeat the procedure. So that is the first case, that is when bed slope SC is given, how to design a canal. So basically design means you're going to calculate what is the depth, what is the width. Okay, you're going to calculate depth and width of the channel. So the next case, that is the case number 2, is when B by D ratio is given, when discharge and the side slope M and B by D ratio is given. So how to design the canal? So first step number 1 is you have to calculate the area in terms of depth, because so they'll give the B by D ratio like 0.5 or 0.75 like that. So let us assume that here for a general case we are assuming it as X. B by D is equal to X. So B will be equal to what? D into X. So you have to find out area in terms of depth. So area is BD plus ND square. You substitute B here, okay, in place of B as dx. So you'll get area as xd square plus 0.5 d square, because n you have to assume. So n you assume it as 0.5. Okay. So that is the step number 1. Step number 2 is you have to calculate the depth using the discharge equation. Q is equal to area into velocity. Here they have given the discharge. Okay, so you will be having area in terms of d here, and velocity, you know the equation, critical velocity, Kennedy's equation, that is 0.55 m d per 0.64 m they'll be giving. So you substitute m also, and substitute both area and velocity in the continuity equation. So you will get the depth. Substitute the q value also, so you will get the depth from step number 2. Okay, and after calculating the depth, what is the step number 3? So you will be knowing depth, calculate the B. You have to calculate the width of the channel and also the hydraulic mean radius. So by using the relation, that is R is equal to A by P. So once you get this, because in the previous step, if you see here, you will be getting D here. Okay, so once you get D here, so substitute this in this particular equation, B is equal to D into X. You will get the width also. Once you get the width, you can calculate the perimeter. And once you get the perimeter, so you can calculate the hydraulic mean radius. R is equal to A by P. That is the step number 3. So once you calculate the hydraulic mean radius, next what you have to calculate? You have to calculate the velocity from Kennedy's equation. That is, because you will be knowing the depth. You'll calculate the depth. So calculate the critical velocity. So next step number 5 is, so once you know this critical velocity and the hydraulic radius, you have to determine the slope, because slope is not given. In the first case, slope was given. So in this, slope is not given. So you have to find that slope from the Kutter's equation. So I hope you already know the Kutter's equation. Okay, and also that particular equation, you have to solve it by trial and error method. So if you see the equation, so the equation is V is equal to C root R S. So you'll be knowing V, okay, velocity. So you can just solve the S using this particular equation. So like trial and error method also you can use. So just simplify the equation, substitute N value, R value. So you calculate, yes, that is the bed slope of the channel. So this is a second case of a design of a canal by a Kennedy's method. And in this Kennedy's method, there are some drawbacks. Let us see what are the drawbacks. See, he have not, he did not notice what is the importance of B by D ratio in his equation. That is a one drawback. So that's why this theory is aimed to design only an average regime condition. Means regime means it's a stable condition. So his theory can be used to design average stable channels or a canals. And also he have not given an account for the silt concentration and also the bed load. He have not taken into account. So, and the complex silt carrying phenomena was incorporated in a single factor M. So because you have not given a more importance for the silt concentration, so you have just included a single factor with a M. So that is one of the drawback. And also silt grade, silt charge were not defined properly, were not defined, and Kennedy did not give any slope equation. So to calculate the slope, he have not given any equation, and he have used just Kutter's equation for determining the mean velocity. So whatever the limitations of Kutter's equation were there were all incorporated in a Kennedy's theory. And also the value of M was decided just arbitrarily, because there is no method or equation which you have proposed to determine that value. And in this method, this theory is basically based on the trial and error method, because especially the second case, the finding out the slope value is takes into account the trial and error method, so which is a very tedious process. So that is all about the Kennedy's method of design of canal. So let us see the second method in the next class. Thank you all.